Hello there, welcome back to the Ephemeris podcast. I'm your host, Aphelion, and it is a new year for the podcast. Get excited, we got a lot coming up this year. Um, we've also got a new season, which is pretty much going to be, I think, the primary focus for this year as well. It's going to be under Chapter 2 of the Ephemeris, so what we're classifying as Chapter 1 is basically the last two seasons, which are a little bit more foundational, and about some very basic stuff that we can build on. And so chapter 2 will now be all other seasons that build on chapter 1. So season 3 of chapter 2, which we are going to be in right now, will be about current news in space science and contemporary discoveries. And if we switch directions, we'll go into season 4 while staying into chapter 2. And as for chapter 3, that is a very, very unlikely thing that will come about in the history of this podcast. So, anyways, it's time to get started with this new season. So, I think the format for these episodes is basically just going to be we're going to go over 3 news stories every single week, and I have quite a few piled up. Some of these articles might be a little bit dated, like maybe a couple months, because I am taking some stories from a little bit further back because I still want to cover them. And yeah, they're basically just stockpiled. Some of them are going to be older, some of them are going to be newer. That's mostly my point. So the 3 news stories we have today. So the first one we're going to start with is the discovery of the most distant molecules in the universe through observation. One of our stories is going to be on long gamma ray bursts, and the other is going to be on the constancy of gravity in the universe, which is going to be a nice segue, I guess, from what we were talking about in season 2. So let's start with the first story we have this week. So using the James Webb Space Telescope, we were able to discover molecules in light that traveled from 12 billion light years away. It'd be really cool if these molecules were like, rare isotopes, or like molecules with rare isotopes, or something that's not seen very often in the universe, really heavy elements. But they were sooty molecules in the end, so not the most exciting type of molecules, but still an exciting discovery. And if 12 billion light years isn't already quite hard to imagine, that means that the light we received from the molecules, or which had the molecules, started traveling when the universe was 10% of its age. So that is really, really old. These molecules were found to come from a distant galaxy, which was observed using gravitational lensing. And I've mentioned it before, but for the record, let us be clear on gravitational lensing. So it occurs when a mass in front of a source of light bends the light coming from the light source. And this isn't, slight warps that occur with your typical convex mirrors and can be traced using focal points. No, this is a complete bend of light, and it happens around a focal line rather than a focal point. And so when the light is closest to the point mass's center, that's when a lot of bending happens. But if it's further away from the point mass's center, that is, in front of the light source, then there will be slightly less bending. So there are 3 types of gravitational lensing. The strong version, or the strong type of gravitational lensing, creates what are known as Einstein rings, and they're just basically visual rings that are named after Einstein, and sometimes it'll produce multiple images. So that is the strong type, and then there's a weak type, which is just going to create some stretches and distortions here or there. The third version is known as microlensing, and this one is where the light coming from a source is not bent, but it is dimmed in, a certain amount of time. Whichever form of gravitational lensing, it does show that light follows paths in accordance with curves in space-time. So that's a little bit of relativity for you there. A great example of, observing gravitational lensing is what James Webb Space Telescope has done with some huge, like, wide field images that it's taken before. Um, and, like, if you were to simulate the passing of a black hole in front of a galaxy, this effect would be um, very, very obvious, and it would be easy to imagine. So, yeah, that's gravitational lensing. And so, in this situation, it helped magnify distant galaxies that were being observed by James Webb Space Telescope, which means that astronomers were better able to see the distant galaxies in terms of detail and find the light that we speak of that has soot-like molecules. So, what's interesting is that these molecules haven't been found or haven't been linked to star formation by scientists. And you'd imagine, or we'd love to believe, that there is a relation between star formation and these soot-like molecules, because it is possible that stars on the AGB sequence, or long-period variable stars on the red end of the spectrum, might be able to produce these molecules, but we do not have that link here according to the scientists. But there is still a impact that this discovery has, and it's the fact that for a long time the distant past of the universe has remained quite obscure. Like, we found quite a few celestial objects that are from the early universe that have heavily redshifted light, like, quasars, or even galaxies. But mapping, like, genuinely and thoroughly mapping the distant universe and the early universe is a tough task, and so finding molecules in a galaxy could unlock a new level of understanding for this type of stuff. And there's a nice statement by one of the researchers in the articles. It goes, quote, "These are the early days for the Webb's telescope." So this article might be a little bit dated, a little bit from like 2022 or 2023, but I digress. These are the early days for the Webb telescope. So astronomers are excited to see all the new things it can do for us. Now that we've shown this is possible for the first time, we're looking forward to trying to understand whether it's really true that where there's smoke, there's fire. Maybe we'll even be able to find galaxies that are so young that complex molecules like these haven't had time to form in the vacuum of space yet, so galaxies are all fire and no smoke. The only way to know for sure is to look at more galaxies, hopefully even further away than this one. So, yeah, cool little story about figuring out some, the molecular makeups of galaxies. So that's our first story. Our second story is on long gamma ray bursts, or GRBs. I don't know which one I prefer to say, but I think I'll stick with gamma ray bursts. So, what are gamma ray bursts in the first place, besides, the whole long gamma ray burst stuff? So, in general, they are humongous explosions, and I'm talking possibly the most powerful explosions in the universe type of humongous. In more formal terms, a gamma ray burst is an electromagnetic effect, as suggested by its name, which occurs due to supernova. So, yeah, it's kind of an emission from a huge celestial event like a supernova. There are two common ways supernova produce gamma ray bursts, which also correlate with the two types of supernova themselves or have some similarities. So, one way is the way that more common type 1 supernovae form. And so it'll be a white dwarf binary, and it'll implode because it's it's got a, would you call it a symbiotic relationship? No, because it's not a symbiotic binary, but basically white dwarf orbiting a sun-like star, and this is a carbon-oxygen white dwarf, and it becomes too massive because it's stealing some stellar matter from the sun-like star, and so it'll explode. So in that process, when the white dwarf implodes, the electromagnetic event that is gamma ray burst will occur. And the other way that a gamma ray burst will occur from a supernova, is the implosion of a large star, which produces a superluminous supernova, which Type 2 supernovas are technically the implosion of a large star, but they're going to be smaller than these implosions. Because they're superluminous, these stars have to be way bigger than type 2 stars. So type 2 supernova are not the same as this sort of method of creating a gamma ray burst, but there's similarities, is my point. There are other producers of gamma ray bursts, including the merging of two neutron stars. We've talked about neutron stars previously on the podcast, and the one very, very memorable thing about them is the amount of momentum they have. And so if you imagine that two of these very, very momentous stellar remnants kind of collide into one another, you'll imagine that, there might be some huge emissions that come out of that, and gamma ray burst is one of those things. So in terms of the time that a gamma ray burst lasts, because it is ultimately a quick emission that happens from sort of a huge event in the universe, it's very short. They occur very, very far away from us. Like, there are not many occurrences of gamma ray bursts in the Milky Way galaxy. And also, gamma ray bursts only last usually about like 10 seconds or less. But there are some gamma ray bursts which occur that are very, very long, and I'm talking like several hours, which is a lot more than what is common. And so now, going into the article, it states, quote, cutting-edge computer simulations combined with theoretical calculations are helping astronomers better understand the origin of some of the universe's most energetic and mysterious light shows, gamma ray bursts, or GRBs. The new unified model confirms that some long-lasting GRBs are created in the aftermath of cosmic mergers that spawn an infant black hole surrounded by a giant disk of natal material. So there's a new source to some of these very, very long and extreme GRBs out there, and we're calling them quote-unquote cosmic mergers. So let's start with that. What in the world do we mean by cosmic mergers? Very simply, we are talking about the collision of two very dense objects. And guess what? We already talked about one cosmic merger, and that is the two neutron stars colliding. So that's actually going to qualify under one of the sources of these long gamma ray bursts based on the definition that's given in the introduction here. There's another cosmic merger that is mentioned in the article, and it is a black hole and a neutron star. So either way, it's probably going to be a binary system with a neutron star somewhere in the mix. Additionally, there are some more details that were found about these long gamma ray bursts. They're said to emerge from jets that form from cosmic mergers. And not only that, but after the cosmic merger event occurs and the gamma ray burst is released, quote, the objects create a black hole surrounded by a large accretion disk, a rapidly rotating donut of magnetically charged leftover material that can pump out long GRBs. Which is pretty nuts. If you start with a black hole and a neutron star, who knows, it might just tear up the neutron star and produce long gamma ray bursts. And that's some very, very interesting, there's some interesting findings, the fact that that's possible. And the effect of the discovery is as follows, and this is a quote from the article that was said by one of the authors. Our findings, which connect observations with underlying physics, have unified many unresolved mysteries in the field of gamma ray bursts, says Or Gottlieb, lead author on the new study and a research fellow at the Flatiron Institute's Center for Computational Astrophysics in New York City. For the first time, we can look at GRB observations and know what happened before the black hole formed. So yeah, this is kind of creating a linkage between cosmic mergers and maybe something like a black hole with a large accretion disk. So very, very interesting stuff in that second story. We're going to move on to the third story, which is the constancy of gravity in the universe. So we're going to take a little bit of a turn towards some theories about the universe itself. So we have an article that are about findings that support the idea that gravity has been constant throughout the universe. But we need a decent amount of context to even understand what this article is referencing. And at first, for the most of the 20th century, general relativity and Einstein's theories told us that gravity has been constant throughout the history of the universe. And just to be as clear as possible, when I talk about general relativity, I just want to go over it one more time because I realized that previously my wording may have caused confusion, even though it kind of made sense to me. Because sometimes that's how my research goes. I will just look something up, try to digest the information, simplify it as much as possible, but some errors will occur. So I did I kind of had a second look at general relativity, and I realized, I should probably phrase some things a little bit better than I did before. So why don't we do that here? Einstein's theory of general relativity, which incorporates the equivalence principle, which we talked about, states that space-time is altered in the presence of gravity. So it's mass that curves space-time, which you can imagine is sort of a fabric that holds the universe, and mass produces a gravitational field, let's call it, that influences the geometry of space-time. So it's mass creates, I guess you could call it gravity, which bends space-time, and its geometry. And so the acceleration due to gravity, as we call it, is a result of the intensity of the gravitational field and curvature of space-time caused by the Earth. So that's the idea. So it like inertial mass times acceleration in the way we think about it in classical physics when we look at it through the lens of general relativity is just your gravitational mass, which is pretty much just your inertial mass, times the intensity of the gravitational field, which, I mean, if we're talking about free fall and acceleration due to gravity, that's caused by the Earth. So the force of gravity you feel on Earth is just your mass following the curvature of space-time caused by the Earth, which is another way of putting that. And so the main sort of gist of general relativity in terms of kind of incorporating gravity is the fact that it shows gravity is not an attractive force in the way that Newton imagined it. So that's general relativity in a nutshell, in some more in better wording, or I'd imagine better wording. So up until the 1960s and 1970s, these ideas justified most of the universe's physics, but then it was discovered that the gravitational effects of massive structures like galaxies and galaxy clusters did not accord with their observed mass. So this created a gap in general relativity that had to be accounted for by some other matter, and so this is where the idea of dark matter and energy spawned. Dark matter is matter that isn't visible to us that will interact with regular matter using gravity to produce the effects we see in galaxies that, general relativity was not able to kind of account for. And dark energy is pretty much just a catalyst for the observed expansion of the universe seen in the last 5 billion years or so, because using the Hubble Space Telescope, we're actually able to see, okay, the last 5 billion years, it looks like it's been a little bit different from the last 8 or so billion years, because it's actually grown faster and faster, or expanded faster and faster, because apparently gravity kind of restrained the universe a little bit for the first 8 billion years, but after that, gravity was less of a restraint. So those are some of the ideas that we have in the modern day. Also, I should mention the only problem with filling the holes in the model of the universe this way, which was not covered by general relativity. The only problem with it is that, we have not directly observed dark matter or dark energy yet. We have created methods in which we use different types of galaxies to observe the effects of dark matter, such as low surface brightness galaxies, but we have never actually observed dark matter and energy. So this is where our article comes in. In the current day, we still accept dark matter and dark energy, especially because of what I said, Hubble showing the expansion of the universe being continually growing. But the International Dark Energy Survey collaboration had some findings that I guess you could say beg to differ. The DES, as I will abbreviate it, collaboration comprises researchers from universities and institutes in the US, UK, Canada, Chile, Spain, Brazil, Germany, Japan, Italy, Australia, Norway, and Switzerland. And people from all of these countries came together to conduct observations and get to the bottom of whether it was true or not that relativity didn't fully account for the expansion of the universe as has been said for several decades. Some details that were given in the article itself, quote, they used the Victor M. Blanco 4-meter telescope at the Chirotellolo Inter-American Observatory in Chile to observe galaxies up to 5 billion light years away. They hope to determine if gravity has varied over the past 5 billion years since the acceleration began, or over cosmic distances. They also consulted data from other telescopes, including the ESA's, European Space Agency's, Planck satellite, which has been mapping the cosmic microwave background since 2009. They paid close attention to how the images they saw contained subtle distortions due to dark matter, so maybe we would call that weak gravitational lensing or weak gravitational lenses. As the first image released from the James Webb Space Telescope illustrated, scientists can infer the strength of gravity by analyzing the extent to which a gravitational lens distorts spacetime. And we've talked about that, right? How really relativity is really, really important for all of this stuff. So far, the DES collaboration has measured the shapes of over 100 million galaxies, and the observations all match what general relativity predicts. The good news is that Einstein's theory still holds, but this also means that the mystery of dark energy persists for the time being. So, yeah, with everything said and done, it looks like Einstein's theories might truly stand the test of time despite all the doubts, and sort of creating these theories that would sort of fill the holes, supposedly, of that, or the holes that general relativity left. But yeah, that's interesting, because if we continue like this, where we're like, okay, it's becoming more and more clear that Einstein's theory is predicting all of these things correct, are we really reversing like 50 or so years of the acceptance of dark matter and dark energy? Is that what we're doing? Because obviously DES can't find evidence that directly goes against the ideas of dark matter and energy. We simply don't have like solid evidence that it actually exists. Like, we haven't directly observed it. But like, if we continue to verify general relativity, is that going to mean that we're going to kind of rescind some of the ideas that have come up because we thought general relativity didn't cover it? So it's an interesting thought. If you have any thoughts about that article itself, definitely feel free to leave a comment below. Let me know what you think. If there are any other thoughts you had about some of the other stories that we had on this episode, then also feel free to comment about that. And if you enjoy the format for these episodes in Chapter 2, Season 3, then also let me know. That's all I've got for today's episode. Thank you so much for listening to the end. If you made it all the way to the end, I appreciate your support. And if you're new to the podcast, which I'm sure there are quite a few people that might be considering the uptick in my subscriber count, hopefully you guys enjoyed too, and make sure you are subscribed, because this kind of content will be coming out weekly this year and this season. I haven't got much else to say other than that, so I will see you all next week. Later.